Usually when you think about a dictionary, you picture a static physical object, right?
Right, like a big, heavy book sitting on a shelf.
Yeah, exactly. When you need to translate a word, you pull it down, you find the page, you read the definition, and then you put it back.
Hmm.
What you don't do is go down to a printing press, print a brand new copy of the entire dictionary, bind it, open it, look up one single letter, and then, I don't know, throw the whole book into an incinerator.
That would be completely absurd.
Right, over and over again for every single word you read.
It's a hilarious visual, but, the scary part is that in the world of software development, if you aren't paying very close attention to how your code is structured,
Yeah.
you might be accidentally telling your application to do essentially that.
Millions of times a second.
Literally millions of times.
Mm-hmm.
And it is a hidden, silent drain on resources that you might not even notice until your application is suddenly buckling under its own weight.
And that invisible drain and the beautifully simple way to fix it is exactly what we were digging into today. Welcome to the deep dive, where we take complex topics and break them down.
Thanks for having me back. I'm really excited about this one.
Me too. So our mission today, we are looking at a hyper-specific micro-optimization in coding, specifically dealing with CJK character mapping in the Haskell programming language.
Which sounds incredibly niche, I know.
It does, but I promise you, you don't need to be a programmer to appreciate this. We're using a fascinating developer's diary entry titled Notes-on-Haskell-Programming, Part 181, by a programmer named Ang. This was published on July 8th, 2026.
Right, and in this post, Ang is actually following up on a previous diary entry, acting on some refactoring suggestions from a tool called Acelint, which is a Haskell linter.
Basically a tool that checks your code for errors or bad style.
Exactly.
Yeah.
And what stands out immediately in these notes is that this isn't just about shaving off a few milliseconds of processing time.
Right.
It's a really deep look at the hidden costs of doing things on the fly, the gamble of trusting your compiler too much, and honestly, the architectural elegance of doing the heavy lifting exactly once.
It's about organizing a system so that the structure itself guarantees the efficiency rather than just kind of crossing your fingers and hoping for the best.
Hoping the computer bails you out.
Yeah. So Ang is deep into part 181 of these notes, working on a console application. And before we get into the memory allocation issue, the whole how of the fix, we really need to look at what this specific piece of code is actually doing.
Right, the actual work being performed.
We are looking at a typography shift. The code is taking standard, skinny, single-width ASCII characters and converting them to full-width characters so they play nicely with CJK text.
Yeah, and the visual problem this code is solving is quite fundamental to terminal emulators.
Oh, totally.
Because CJK characters, meaning Chinese, Japanese, and Korean characters, are intricate. They traditionally take up a double-width cell in a fixed-width terminal grid.
They're wide.
Very wide.
Yeah.
But standard ASCII characters, your typical English letters and punctuation, they only take up a single cell.
So they're narrow.
Right. So when you try to align standard English text within a grid of CJK characters, particularly in a console application where you might be trying to draw UI borders or align columns of data, the whole layout just breaks.
It gets all jagged.
Exactly. The columns don't line up because the cell widths are totally mismatched.
So Ang's code features a mapping table called single width to double width. And this is that dictionary we were talking about at the start.
Translation guide.
Yeah, it acts as a translator to fix this exact layout issue. And the notes give us some really specific concrete examples of how this translation works.
You do, yeah.
For instance, the standard space character, which the code represents as a simple quote space quote, is mapped to the hex code by 3000.
Right, and Ang's notes explicitly call this an ideographic space.
Which is such a cool term. But basically, it's a full-width space character designed to take up the exact same double cell width as a complex Chinese character.
Exactly. And it handles punctuation the same way.
Oh, right.
The standard left and right quotation marks, X2101C and X2101D, they get mapped to by 300C and by 300D.
And those are the distinctive corner bracket style quotation marks you often see in Japanese text, right?
Yes. They look like little visual right angles.
I know exactly what you mean. It's so visually distinct.
And the code also handles a massive chunk of the keylord using a really clever mathematical loop.
Instead of writing it all out manually?
Right. Instead of writing out a translation line for every single letter and number, Ang's code takes everything from the exclamation mark all the way to the tilde, basically the whole standard ASCII range, and maps them using a mathematical shift called a full-width offset.
Oh, that's smart.
It calculates the new full-width character dynamically just by doing a bit of math.
You know, I always like visualizing this stuff. To me, it's like you have a stage production and you have a cast of skinny single-file actors.
Okay, I like where this is going.
Those are our standard ASCII characters. But they have to share the stage and perform this complex choreography in a strict grid with a cast of actors wearing massive boxy mascot costumes.
CJK characters.
Exactly. And the grid on the stage is the terminal window.
Right.
And if the skinny actors just stand normally, the spacing of the whole dance routine is ruined. The visual harmony is just gone.
Because they don't take up enough space.
Yeah, so Aang's mapping table is the wardrobe department. It takes those skinny actors and gives them all perfectly tailored, identical, massive shoulder pads.
Love that.
Now, every single actor, regardless of whether they are a simple comma or a complex kanji character, takes up the exact same amount of stage space in that terminal grid.
They are handing out digital shoulder pads so the English punctuation can stand shoulder to shoulder with the CJK text.
Exactly.
It really does solve the layout problem beautifully. But, the mapping table itself, the actual translation dictionary, isn't the core issue Aang is writing about here. The logic is sound.
The dictionary works.
It works perfectly. The problem comes down to when and where you ask the program to read that dictionary.
Ah, right. This brings us to what we can call the GHC gamble. We are moving from what the code does to how the application was initially structured to use it.
Yes. In the original setup of Aang's code, you have these pairs of characters, the single-width character and its full-width equivalent. Now, in Haskell, especially for high-performance string manipulation, you don't typically want to pass around raw string types.
Why is that?
Because standard strings in Haskell are notoriously just linked lists of characters. They're very inefficient for this kind of work.
Okay, so what do you do instead?
You want to convert them into a more efficient, tightly packed data structure, and the code does this using a function called tpack to pack those characters into text objects.
Got it. And in the old version of the code, this packing process was happening in a file called converter.hs.
Which is the calling module.
Right, the part of the program actively doing the work of tidying up the strings. So when the converter module was handed a messy string of text, it would look at the dictionary, apply that tpack function to create the text objects, and then execute the replacements.
But Aang realized there was a major invisible risk lurking in that specific structure.
The gamble.
The GHC gamble. The Glasgow Haskell compiler, GHC, is incredibly sophisticated, but it operates on certain rules regarding when and how it evaluates expressions.
And Aang realized that depending on how GHC optimizes the code, a local variable called tidy pairs might be reevaluated and reallocated in memory every single time that tidy function is called.
Meaning, every time a new string comes in to be formatted, the program might be going back to the raw dictionary, running tpack on every single entry to build the usable text objects, storing them in a new chunk of memory just to process that one specific string, and then
Checking the book in the incinerator.
throwing it all away. Exactly.
Aang actually explicitly notes this in the diary, saying, perhaps it is optimized by the compiler to be evaluated at least once memoized, perhaps.
But the uncertainty is the entire point. In Haskell, if a value isn't lifted to the top level or explicitly cached, the compiler might just decide to recompute it on every single invocation.
Okay, I have to push back here, though. Let's say the compiler doesn't memoize it.
Okay.
Let's say it does reevaluate tidy pairs every time. We are talking about modern CPUs here.
Right.
I've got an M-series chip in my laptop that can brute force billions of operations in a second.
Oh, absolutely.
I mean, L1 and L2 caches are massive today. Branch prediction is incredibly smart. Does it really matter if converter.hs retranslates a few dozen text pairs on the fly? Surely the computation time for a basic mathematical offset and a few tpack calls is practically microscopic. Are we over-engineering a problem that modern hardware already brute forces for us?
I get that, and if we were just talking about raw CPU cycles for the mathematical offset, I might actually agree with you. The CPU can calculate that offset in its sleep. But you're missing the crucial bottleneck in a pure functional language like Haskell.
Which is?
Allocation. It's not the math that hurts, it's the memory management.
Ah, because tpack isn't just doing math.
No, it's not. It's building a brand new data structure.
Oh, I see.
Exactly. tpack is actively allocating new memory to create those text objects. If this console application is processing a massive log file or formatting streams of data in real time, and it's reevaluating that dictionary for every single line.
It's requesting new memory blocks millions of times.
Millions. This creates immense memory pressure on the system.
And memory pressure inevitably leads to garbage collection.
That is the real killer right there. The runtime environment has to constantly pause your application, scan the heap, find all those discarded dictionaries you threw in the incinerator, and free up the memory so the program doesn't crash.
Oh, wow. So it literally stops the work.
Yes. Those garbage collection pauses compound. They completely destroy your throughput. Your CPU might be blazing fast, but it ends up sitting idle, just twiddling its thumbs, while the garbage collector cleans up the mess your inefficient architects are left behind.
That makes total sense. So relying on the GHC compiler to hopefully memoize the work, like hoping it magically realizes it should save the dictionary, is a massive gamble.
A huge gamble.
You are crossing your fingers that the compiler's black box heuristics save you from your own memory allocations.
And a good engineer doesn't hope the system is efficient. They architect the system so that it has no choice but to be efficient.
I love that. Which brings us to the climax of Ang's diary entry, the architectural shift.
The fix.
Yeah, Ang decided to eliminate the compiler gamble entirely. To do this, Ang moved the responsibility of converting the character pairs into text objects completely out of the ActiveConverter.hs module.
Right. Pushed it away from the active line of duty.
And pushed it back to the definition module, the file where the dictionary is actually defined, which is called lexicon.hs.
Let's look at the Haskell code Ang uses to accomplish this, because it is wonderfully succinct.
It really is.
In lexicon.hs, Ang writes -map, bimap, tpack, raw pairs.
Okay, let me make sure I'm parsing that correctly.
Right.
Raw pairs is the underlying list of the single width to full width characters, right?
Yes, the basic raw dictionary.
And the map part applies an operation across that entire list.
Exactly.
But bimap is the really clever part. It allows you to apply a function to both elements of a tuple simultaneously. So bimap tpack is basically telling the program to hit both the left side and the right side of the character pair with the tpack function.
You've got it. It creates a fully packed, ready-to-use tuple of text objects. But, the genius isn't actually the bimap function itself.
No.
No, the genius is the scope of where this code now lives. By binding this evaluated list to a top-level name in lexicon.hs, GHC has very strict rules about how it handles it.
Because it's at the top level.
Yes, top-level values without arguments are evaluated exactly once.
Oh, so the compiler no longer has a choice.
None at all. It is structurally mandated. The mapping table is fully constructed, packed, and ready to go exactly once, likely when the module is first loaded.
And Ang points out the ultimate result in the notes, writing that the mapping table is now stored in memory for the entire lifetime of the console application.
It's beautiful.
No more on-the-fly allocation, no more garbage collection thrashing.
It's truly the holy grail of this kind of optimization.
I think about this like a restaurant system.
Okay, lay it on me.
So Converter.hs is your line chef. They are actively cooking meals during the dinner rush, taking incoming strings and formatting them.
Very high-stress environment.
Exactly. Now, the old way the code was written forced that busy line chef to stop, grab a whole unpeeled onion, chop it up, use a handful of it for a dish, and throw the rest away.
Oh, that's painful.
Right. And they had to do that every single time a new order ticket came in.
The line chef is doing the work of the prep cook, and the kitchen just grinds to a halt.
Absolute chaos.
Okay.
But by moving this packing process to lexicon.hs, Ang essentially built a dedicated prep kitchen.
Oh, I see where you're going with this.
Yeah, they use that bimap function to have the prep cooks peel and chop all the onions, perfectly portion them, and put them in containers before the restaurant even opens its doors.
Before the program even starts processing text.
Exactly. Now, for the rest of the night, the lifetime of the application, when an order comes in, the line chef doesn't chop anything. They just reach over to the prep station, grab the pre-chopped onions, and throw them in the pan.
The line chef is purely executing, not allocating raw materials.
Yeah.
That visualization really highlights the beauty of this refactor.
That makes it so clear.
It really does. Ang completely removed the GHC compiler optimization guesswork. By moving the heavy lifting to the prep kitchen, the architecture itself becomes inherently efficient.
Right.
The compiler doesn't have to guess if it should save the dictionary, because Ang built the dictionary into the foundation of the building.
It is incredibly satisfying when a structural shift solves a performance issue that elegantly. I mean, we started with a typography problem. Formatting ASCII, quotes, and spaces, so they align perfectly in a terminal emulator alongside double-width CJK characters.
Which is a cool problem on its own.
It is, but then we saw how the initial implementation, while logically correct, created a massive hidden tax on the system's memory management because the active module was allocating text objects on the fly.
And then we arrived at a beautifully simple fix.
Moving the computation to the definition module, creating a static, permanent table that exists for the lifetime of the program.
Transforming a compiler gamble into a lifetime guarantee.
I love that phrasing.
You know, something that I find genuinely inspiring about this source material is the very last sentence of Eng's notes.
Oh, right, the ending.
Yeah, after going through this entire process, identifying the memory pressure, moving the code to lexicon.hs, and achieving this elegant structural fix, Eng writes, "Can we still improve this code further? Yes, and I was surprised we can even refactor or simplify this even more."
So even after all of that analysis, there's still more blood to squeeze from the stone.
Always. But Eng saves the details of that final simplification for the next post.
It's a literal cliffhanger.
It is. But it perfectly captures the mindset of a great software engineer. The pursuit of optimization is never truly finished.
No, it's a constant process.
You solve the immediate bottleneck, you restructure the architecture, and then you look at the new baseline and ask, okay, what's next? There is always another layer, another abstraction to refine.
Which brings me to a final thought for you to mull over today. We've spent this time talking about Haskell memory models and compiler heuristics, but consider the architecture of your own daily workflows.
That's a great point.
Think about the recurring tasks you tackle, the complex problems you face every week. Are you relying on the compiler of your own brain to reevaluate, relearn, and reallocate your mental energy every single time that familiar problem pops up?
Are you chopping a brand new onion for every single email you write?
Yes, exactly. Or is there a way you can build your own personal lexicon module? Find the hard translation work, do it exactly once, build a template or a system, store it in your memory, and let it serve you for the lifetime of your career. It's definitely worth a deep dive of your own.